Hello, good morning, good evening, good afternoon, everybody, where you might be. It is my great honor and pleasure to welcome my old friend and colleague, STEFAAN, who came to us all the way from the capital of Europe, all the way to Warsaw. So STEFAAN will speak about aspects of the formal theory of monads, including adjunctions, entwining structures, structure enlacée en français, and Galois theory. The Zoom is yours, the floor is yours, take it away.
Okay, thank you very much for the kind invitation. It is nice to be back in Warsaw. My last visit was more than 10 years ago. So then that was at the occasion of the yearly meeting of the presidents of the National Mathematical Societies of European countries, which took place here at CAENEPEEL. That was also nice. And the first time I was in Warsaw was way back in 1985. These were really different times, but I still remember it very much. And now in my room here, I have a view on the Palace Cultura. Yeah. And the Department of Mathematics of the university in those times, 1985, was in there on the 10th floor or something. Yeah, I remember it very well. Okay, so what I'm going to be talking about, it is work in progress. I gave a lecture about 1 month ago on a meeting in Cluj-Napoca in Transylvania. And some good things are in it, but still not all questions are answered. And I should mention also that this morning I received an email from Joost Verkruijsen, who apologized for not being here, also not online. Mm-hmm. But he talked about the problem together with Pepe Gomez some time ago. And there is even a preprint which I had never seen before, but he sent it to me and I had a look at it today. So now we need to talk together and see what can be done. Probably this will be a joint project. So let me introduce now with the, let's say now, classical theory. So this follows an idea of Brzezinski. So he realized the importance of codings in some branches of algebra, and he managed to give a very nice formulation of several aspects of Galois theory in terms of codings. So let me recall that briefly. You work over a commutative ring K, you consider a morphism of K algebras, and then you take an A coding, and then there is actually a misprint. So this is a co-algebra, or equivalently a co-monad in the category of bimodules. You can have two structure maps, co-multiplication and augmentation. And then you can introduce the category of right comodules. And you can introduce the notion of a group-like element. So this is an element X in the coding, such that delta of X is X tensor X, and epsilon of X is equal to 1. And then, if you have such a group-like element, you can make A into a C comodule on the right and also on the left. On the right, you do it by sending A to X, A.
Sorry, I have a question. So you are regarding algebra as a monad in the category of bimodules. So you are anticipating two categorical language for monads, but in this monoidal category, it's simply a monoid. Am I right?
Yes.
Yeah. Okay.
Yeah, this is a question of terminology. Mm-hmm. Yes, indeed, anticipating, you can view the category of bimodules as a two category or a bicategory with one object.
Yeah.
And then it's okay. Then we make an assumption. So morphism of K algebra that you have, you assume that it factorizes through the co-invariance of A. And you can restate this by saying that A, so it is left B module by restriction of scalars and a right C co-module. And that the two structures are compatible with each other. Okay, in this situation, you have an adjunction from the category of B modules to C co-modules to the right. You work on the right side. You send the module N to N tensor Bm, N tensor Ba, there's another misprint there. And the other functor is given by co-invariance. And then the question is, when is this a category equivalence? And then I will generalize this, but it is quite easy to prove from general arguments that if the functor f is fully faithful, then this I from B to the co-invariance is an isomorphism. So B is the co-invariance of A. And if G is fully faithful, then a certain map called the canonical map. In this sense, A tensor A prime to the following, you take the group-like element and you multiply to the left by A, to the right by A prime. And in this situation, C with X is called the Galois.
Wait a second. I want to make sure that I understand the notation. So C is a covering over A, right?
Yes.
Okay. And B is what? Coaction invariance? No. What is B?
In the beginning, there is a morphism, an algebra morphism from B to A.
Okay.
And an assumption is that this factorizes through the co-invariance of A.
Okay.
And then, in this general situation, you still have an adjunction.
Okay. Okay. Mm-hmm. Yeah, thanks.
I have another question, some notational problem. So this M upper C, so this is, so first of all, it is assumed that they are A modules.
Yes.
And this is this.
One could
Category.
write
Why A is missing here? Yeah. Because it's in Eilenberg category for this Monads C, but on the category of right A modules.
no, the category of C.
Yeah.
Yeah, it is on the category, yeah.
So A is hidden here in this notation.
Yes.
Well, it's fixed. Like okay.
Well, it is not,
fixed as
it's
well.
not hidden in the sense that C is supposed to be an A covering.
Yeah.
The A is there.
So also K is the base ring is hidden.
Okay.
And I understand that now, if you want to make a coaction on this f of n, right, because it's supposed to be a covering comodule, then it's what you map it into one.
You put the coaction on A induced by the group-like element.
Group-like element. Okay. Okay. Mm-hmm. Yes, of course. There's no one.
Okay. So these are necessary conditions. The next thing is, when are these sufficient conditions? And there you can proceed as follows. You take one example of the coding, which is called the Sweedler canonical coding. What you do is you take A, tensor A over B, and the co-multiplication, you obtain it by putting one tensor 1 in the middle, and epsilon is just multiplication.
A stupid question. Was it really a Sweedler who constructed this coding, or is it just, baptized after him? Like Levitt pap algebras are definitely not due to Levitt.
I believe that Takeuchi attributes it to Sweedler.
Really? Okay. Okay.
Yeah, there is okay, so then you have the canonical map. This lands in A tensor A. It turns out to be a morphism of codings, classical sense. You have one tensor one being a group-like element of A tensor A. So what I just did in general, you can do for the Sweden canonical coding. So you get a new adjunction, KR, between MB and MD.
You agree with my correction? I just wrote the correction on it.
Ah, okay.
Right.
Okay, and this was basically studied already a long time ago. This goes back in commutative setting to Grothendieck, but then in algebraic geometry. There is a very nice description of it in the lecture notes of Cousineau and Goeren from 1974, also in commutative case, not with the language of corings, but where essentially it is shown that this gives you a pair of inverse equivalences, provided that A is faithfully flat over B.
So ERA is commutative or no?
No. This generalizes to the non-commutative setting. In the commutative case, the notion of coaction you can simplify a little bit, and that gives you the descent data, which are originally called described by Grothendieck in the scheme theoretic version, translated to the affine version by Cousineau and Goeren, which correspond to co-modules of the Sweetener coring. And in the non-commutative setting, this is in a paper by an Italian, something in the 70s. So then there is a paper which generalizes this to the non-commutative setting. So this is basically known, and it's algebraically spoken also the most important. And then you have immediately the following thing. Suppose that A is faithfully flat as a B module. And suppose that the Galois coring is Galois, C. Then of course, since C is isomorphic to A tensor A, you have isomorphism of the co-module categories. And then the two adjoint pairs are basically isomorphic, and then if one is an equivalence, then the other one is also an equivalence. And this is the way how you can.
Yeah, so this is a consequence of the Beck theorem.
Yes, and the Beck theorem is there.
And I have something to say about Piotr's question, that this construction is a construction of the following way, of the following sort. You have an A, which is a monoid in the category of B bimodules, and you make from it a comonoid in the category of A bimodules. So this construction appeared in descent theory, when people started speaking, even in topology, when people started to speak about how is it called, this bar and cobar construction. So the roots of this construction is, in fact, in algebraic topology. Maybe the 50s.
That's quite possible.
Now, correct me if I'm wrong. I'm staring at the conclusion, and what I see in it is that it should be generalizing very old but fundamental theorems of Schneider, which tells you that if you have faithfully flat copical extensions and you have the next slide.
Exactly, that's the next slide.
Sorry, I maybe need to close it. Right again.
Hopf algebra correction.
So, the very classical Galois theory, where you have an action by a finite group on an algebra, and then it turns out you can associate it with a coring that is is Vrije as a left S module. Okay, and there is the Galois descent theory. That is then a special case of what you have. It's not the only one. You can also take a graded ring. That is means a coaction of a finite and then possibly of an infinite group. And you can associate them also according to it. So as a left module, it is isomorphic to the, well, this looks the same as the previous one, but with different multiplication. And there you obtain the result that for, so then a Galois sees Galois if S is a strongly graded ring. And that gives you the well-known theorem about strongly graded rings. And then generalizing the, well, in fact, generalizing the graded ring theory, you have the half-Galois theory. So then the coding is of the type C is A tensor H. In this case, it is S tensor KG, if you want.
Sorry, so the passage from the first to the second is like dual point of view.
Yeah.
First is about actions and the second coactions.
Yeah, and the Hofgawa theory, and that is already in the book of Chase and Sweeder. So that is in fact about coactions. And then that is hidden a little bit in the lecture notes of 1968. You have to do duality to go to actions. And the advantage of coactions is that you can apply it in infinite dimensional case. Whereas for Galois theory, you need finiteness. And in this case, so this is also a special case of this. You pass through the dual Hopf algebra. And if you start with the one that is finally generated projected in the dual one, use it also, and then it all matches. Then another generalization that will be important in the sequel, the coalgebra Galois extensions of Brzezinski and Agit. Their C is of the type A tensor C, where C is now a coalgebra. Which is also the case in the previous case, when it is a Hopf algebra, it is in particular a coalgebra.
Plus entwining, otherwise
Plus, yes. But entwining, and then you can go further. The Brazilians, Dokuchaev, well, who is a Russian that went to Brasilia, Ferreira and Paques, they considered partial actions of groups, well, of finite groups, I should say here. And they introduced the Galois theory for this, and that also fits in the schedule. But there now you have to take a quotient of this one, of the classical one. Hopf Galois theory for weak Hopf algebras. This was done by myself and de Groot, my former PhD students. Also that fits in, and there you also have a quotient of A tensor H. And then quite recently, Baggio, Paques, and Tamusianas, they considered partial actions by finite Grupowitz. Well, and I should say that the work of the Brazilians, that did it from the algebraic point of view directly, the fact that it fits in the scoring setting, this was done by myself and de Groot in the case of partial actions of groups, and by myself and Timmy Vieremans in the case of finite Grupowitz. And you could even go further, finite Grupowitz. You could consider the Hopf categories that I considered not so long ago together with Verkruijsen and Batista. And also something that I introduced, so you mentioned entwining structures. You can consider weak entwining structures. I will make a remark about that later on. They were introduced by myself and de Groot, and also there you can, that fits into the schedule. So you have a very large schedule.
Sorry, so something is missing on this list. So we are coming back to actions. Why not to speak about coactions?
You can.
Okay. Oh, I.
Okay, I mentioned these because these were done by other people, then we realized that, well,
Because there's an approach by Day and Street about opmonoidal monads. So in this language is an analog of the coaction.
yeah.
Functions on a group.
Okay, actually, what happened is, so these partial actions of groups, once that was at the meeting in Mexico, Herrero gave a lecture about it. And of course, I was tempted to say, how can we do that for Hopfalgebras, which is not obvious. Because of course, Hopfalgebra is something linear, group is something discrete. What does this mean, a partial action? I could do it, and then immediately I had partial co-actions also you can dualize.
Yeah, but I meant this Days and Streets quantum groupoids, which is a language which is dual to groupoids in a sense.
And then you have like partial coactions of quantum point.
Okay, so this is not the end. At the beginning of the century, Layachi, El Caotit, and Pepe Gomez Torrecillas, they introduced Galois theory for combinatoric scorings. What are the data? Two algebras, as before, a coring, but now the two algebras are not connected by a morphism, but by a bimodule. And they assume that it is finally generated and projective on the right side, so that you have a dual and that you have an adjunction, which will be important in the sequel. And then they assume that the original module, the sigma, is a C-core module. And it turns out that this is equivalent, so C-core module structures on sigma are equivalent to left C-core module structures on the dual. And the B, that means that the action by B is compatible with the co-action. And then you can describe this, you can proceed as before. In the situation, in the previous situation of the previous slides, it turns out that the adjunction, so the two modules from the adjunction are A as a BA module and as an AB module by restriction of scalars. So it's a generalization to that situation. And then you proceed basically as in the previous situation, which they didn't do. There is a paper by myself, De Groot and Oosterkruiser, where we do this extensively.
So sorry, so what exactly is comatrix scoring?
The
You
comatrix
see the A scoring and then you have additional data. So how does it assemble into a comatrix scoring? I'm confused.
terminology comes from those guys.
Spanish.
But basically what it is, the comatrix scoring replaces the three canonical scoring. In this, so you have an adjunction, and as we will see later, to an adjunction you can associate the co-monads, and that is the comatrix scoring. And it comes from the fact that if you want to describe a matrix algebra and a matrix co-algebra, there is an adjunction that gives those two, but a very classical one.
But am I too naive in thinking that a comatrix scoring is a special type of a covering or a...
Yes. This is of the form psi or psi star tensor over B with psi.
Yeah, it is omega tensor sigma.
So comatrix scoring is something you build out of another covering, right?
Yeah.
So in particular, sigma would be A.
Yes, and
And
then
you got-
it be sigma star.
Yes, but
Oh, this is sigma, not psi. So-
yeah, it would not be exactly Zwiller because you would have A tensor A star.
But no,
But with respect to A.
Oh, okay.
right module endomorphism.
Sigma finally generated projected as a right A module of sigma is equal to A. As a left B module, you don't know, but as a right A module, it's free of rank 1.
Okay.
So
And then
Because I was thinking at the construction in of algebras where you have A tensor A opposite over the field, and then that is you need the opposite to get off algebraic. So I was thinking about this. You
no, it's
have
not
the
that construction.
yeah.
It is the opposite gives of course the matrix ring.
Yeah.
if you, because look, this is the theory of corings.
Yeah.
What you are talking about is the theory of monoidal monads.
Mm.
Then you have
Very
A
aware of
op.
it.
So the Swidler would be of the form A op tensor A.
Yeah.
But op doesn't make sense here because it's regarded only as A by module.
Yeah.
Monoid in the category of A by modules.
Yeah. Okay.
Yes, A tensor A op is the matrix ring.
Yeah. But
And
A
A
op
op
tensor A over B.
Okay, so what was the intention? So very much of what I presented takes place in the category of bimodules. You can take OK algebras, and they are the basis of a two-category, category of the two-category called bimodules. And the bimodules are the morphisms in the two category, which I will come back to later. So the idea was maybe we can look in bicategories or in two categories and see whether the things can be generalized and maybe also formalism can be simplified. The second thing I think can be done, but then you have to reformulate things a little bit to make things easier. So let me briefly recall what is a two category. So it consists of a class of objects. These are called zero cells, and then for each pair of objects, a category.
The arrow.
That's it. No, it's not my arrow.
It's not your arrow. Okay. Sorry. Yes. Okay.
The category A between A and B, but I write it like this. I write it as BAAA, which makes things a little bit easier, as you will see, because you need functors. And with this notation, so the B is twice in the middle, so you get functors from CAB times BAA to CAA. Like the tensor function. Yeah, like it comes from.
Like the balance over B.
And then you need also unit functors. One is the category with one object and one morphism. And then you need strict associativity and unit conditions, which I wrote on the next slide, but which you can expect what they are. And they are already easier to write down with this. If you look in category theory books like the book of Porsche, they use the classical notation, and then it is a little bit confusing. It's, of course, this is what it should be, but here it is a little bit more.
Sorry,
and there is a bracket.
You like to begin by the like you don't need the closer. I need the closer, like Sheldon Coop.
In the bicategory, these diagrams do not have to commute, but up to a natural transformation, which has to satisfy certain coherence conditions. But then there is a coherence theorem. So this is why I can safely restrict myself to two categories, which are strict. The notation that I will use. So for the zero cells, I will use capital letters. For the objects, in the underlying categories, I will use small letters. And for the morphisms, which are called two cells, I will use Greek letters. And then for the composition, I will either use tensor products or just juxtaposition. It turns out that in many cases it is clear, so you have to be careful, of course, that you can write M tensor N only if the source of M is the target of N. But if you keep that under control, then you can safely delete the tensor product, which makes everything a little bit easier. And the same thing for the two cells. Unit objects on 0 cells and on 1 cell, I denote by the same letter. So you can write 1A, but I use A. And for the identity on M, I just use the letter M. And in some diagrams, you can see easily where you put identities. What are the examples? Well, this is very well known, the basic example, the modifying example, the underlying example is the one where objects are categories. The 1 cells are functors, and the 2 cells are natural transformations. This means the underlying categories are tensor categories, are functor categories. Okay, there are possibly some set theoretical obstacles. Maybe you have to restrict to small categories, but there are ways to go around this by working with union. I never checked all the details of this, but it is known that this can be done. And usually people don't care about it. And then this I mentioned already, you take K algebras, and then the underlying categories are the categories of bimodules. And then a strict monoidal category is just 2 categories with one cell, with 1 0 cell. I'm sorry. Okay, and then there are many things that you can do in categories that you can easily generalize to 2 categories. For example, adjunctions. What is an adjunction? So I write it as a 6-tuple. Here I keep all information. So 2 objects, then 2 1 cells, 1 from A to B, 1 from B to A. And then, oh, I forgot something here. Eta should go from A to Mn, and epsilon from Nm to B. This is something I forgot.
Right. Can you write it with a pen? But first, you have to switch it to the pen. 0.5, black 0.5, higher here, yes.
So. Sorry, this is eta. I hope I'm doing it right. N. No, I think it's wrong.
So instead of A, there should be identity factor.
And Mn is from B to B, so there should be B on the left and A on the right. A and B are exchanged. So Mn is from B to B, and Nm is from A to A. So that is B. The other one is A.
Right. Yeah, it's something. Yeah, and then everything fits, I guess.
Yeah.
By B and A upstairs, you understand identity.
Like this, yeah.
Yeah. all the time.
You have to select the three again. The ones below? No, the one below with the three. The one with three. Yeah. Okay.
Right. So then we scroll to the left adjoint of n. If eta is an isomorphism, then n is called fully faithful. If epsilon is an isomorphism, then eta is called fully faithful. And if you have both, then we have a triple equivalences. Now, adjoints are unique, also in a two category.
So that equivalence would be kind of a Morita equivalence in the example of a bimodule. So two slides back, it's
Okay.
I wanted to understand.
So I introduced. Well, you can also introduce Morita equivalences, and if one of the functors is fully faithful.
Yeah, but if you use the two categories in the example of the two categories with algebras bimodules, what is this equivalence? Is it something known? I want to understand it in one example. So if A, B, and so on are algebras and Mn are bimodules, we are saying basically that they have the same category of modules.
In this situation, you mean?
Yeah, in these two categories.
No, then they are Morita equivalents.
That is Morita equivalence, yes. Okay.
Well, you can, in the same way, you can define Morita equivalence. Then one of the two has to, but they both, the eta has to go in a different direction. Then you have different conditions here.
Yeah.
And then you can show that not the surjectivity is not sufficient because you don't have notion of surjective, but if one of the morphisms splits, then you have a pair of adjoint functors.
Okay.
If one of the morphisms splits, then it is an isomorphism, and then one of them is an isomorphism, then you're in this situation, and so then you have an adjunction.
Okay.
So the adjuncts are unique. This is exactly the same thing as in categories. So suppose you have two adjunctions with the same, between the same objects, and one of the one cells is the same, the other one is different and also different, connecting two cells. Okay, you can construct maps from n to n prime and from n prime to m. They are each other's inverses. And once you know these maps, then eta and epsilon are determined by eta prime and epsilon prime and vice versa.
So this means essentially that, or reproduces this one categorical notion that the left adjoint is uniquely determined up to isomorphism.
And the same thing for the right adjoint, of course.
Yeah, of course.
You can use it, so I included it in the slides, but I won't go, so it enables you to do the duality functor at the level of a two functor in a canonical way. So this is known, but I think it's a nice way to do it. You can organize the adjunctions into a two category. The same objects as the original category, and then the one cells are adjunctions. And then I describe morphisms. So you need an alpha from n prime to n, and a beta from n prime to n, and some compatibility, one compatibility condition, which is isomorphic to one, which is equivalent to another one. You can define composition of one cells. Okay, and this gives you a new two category. Then you have a forgetful functor. You can do that for the underlying categories first. So you forget the adjoint. That gives you a two-functor. A two-functor is the equivalent of a strictly monoidal functor at the level of tensor categories or of monoidal categories. You have a second one for getting the other adjoint, but that goes to the opposite category. Then what you can do, so if you assume that every one cell in the two category has a left adjoint, then you can fix an adjunction for every one cell, and then you can define functors in the other direction. And that gives you another pseudo functor. You can take a composition, and that gives you a functor from A to A opposite, mapping something to its dual, and that gives you a nice explanation how it is functorial. And the same thing you can do in the other direction, you can do in the other direction, and then you have the equivalence. The composition of the two ones is the identity, or is two equivalent to the identity.
So the right rigid is something like having the antipode on the Tanakian level. Okay.
Yeah.
Okay. So in this Tanakian philosophy, if you have something which has right rigid, which is rigid, which means right rigid and left rigid, it means like to have invertible antipode. But what does it mean to have left rigid separated without being right rigid? Is there some analogy in this Hopf-Galois theory for this?
Is the existence of an opposite antipode.
An opposite antipode without antipode.
Yeah.
Okay.
Yeah.
Okay. Okay, you're right.
Yes.
Okay, so this is just the short.
I'm sorry, Steph, but am I supposed to know what the pseudo functor is?
Okay, so I already told you briefly what the two-functor is.
Huh?
So this means you have, between the corresponding categories, you have functors. And then you need a strict, at the level of one object, you mean a strict monoidal category. And then a pseudo-functor, there it is where you don't have the strictness, but where you have connecting isomorphisms. So this is what would be called a strong monoidal category, a strong monoidal functor.
Okay.
For monoidal categories.
Okay.
And then if you drop that, where you have a usual monoidal functor that has the terminology lax functor.
Lax.
Yeah.
Okay. Okay.
So strict, strong, lax.
Yes.
So in the higher category theory, every level is laxer and laxer, weaker and weaker.
Yeah. Okay. So in the two category, you can also introduce monads and comonads. This is like the definition of an algebra in vector spaces, or
Co-algebra.
yeah,
Monad.
or a ring or co-ring.
Correct. Right.
So that is the obvious thing. And they are related to adjunctions. So if you have an adjunction, you can associate with a monad and a comonad. The monad, the underlying one cell is NM. And then the multiplication goes from NM to NM, and you put epsilon in the middle. And the comonad in the same way, but now you have to go from Mn to Mn, and then you put eta in the middle. And then here the unit is eta and the co-unit is epsilon. By the way, it should go back. By the way, I denoted the unit map for monads by iota, not eta, because I want to have that for adjunctions. And the same way, I usually write a modified epsilon, because the epsilon, this epsilon I want to keep for adjunctions. I will come back to the construction a little later, so I have to be careful. Street defines a two-categorical structure on monads. And now I don't know whether this is known, and I also don't know whether this is important, but I think there are some applications. You can do the same thing for adjunctions. You can do that in such a way that the associated construction becomes two-categorical. Okay, it will not be important for the sequel. You can also introduce, and I call them modules and co-modules. Well, from a categorical point of view, they should be called algebras and co-algebras. I don't want this. Okay, this goes in the usual sense. There is something, they are in vector spaces, you do that on one side. So you have the category of right A modules. But that is because on the left you always have K. There's only one zero cell, which is K there. Yeah. But here you have several ones. So there's also, all the time, there is also one on the left-hand side. And the A here should be a lower A. And for co-modules, so as before, so the C is then over B, and there should be a lower B here. And I can tell you right away, so here you have a kind of bimodules on the left-hand side by B, which is B is itself also a monad, and the co-monad, but in the trivial way. On the right-hand side, I have A. If you take that trivial, so it should be A should be here.
You're fine.
And here is the pen.
Yeah, but finger also works. Yeah.
You can put that A also equal to capital A, and then you just have the one cells. Then you should just have the underlying category, the original category. You can
Eilenberg-Moore category.
Yeah.
Okay.
And you can you can also define for two monads, you can define bimodules. But these don't play a role in the street version. But they will play a role later on.
Sorry, so what about Kleisli category? Because it was about Eilenberg-Moore.
You can also do it, but it's
because if you have a monad, then you have all possible adjunctions inducing this monad,
and the other,
bounded by the minimal one and maximal one. One is Kleisli, which is kind of free, and another one is Eilenberg-Moore, which is a kind of all modules over this monad in a sense.
I think you can do the same. But
you can do the same, yeah. Okay.
Okay, but the next step, you take an adjunction, and then the co-monad over B. And then you can look at left C coactions on M and right C coactions on N. And there's a bijective for a correspondence between the two of them. And this is given by these formulas. You can do that in the situation where B is the co-monad associated to the adjunction. And then it turns out to be the right coaction is given by eta n, eta being the unit of the adjunction, and the left one on m is given by n eta, following this formula. Okay, and then without any more assumptions, you can define the canonical map, which goes from Mn to C. And that is a morphism of comonads. And that plays the role of the canonical map that we had before. We had from A tensor A to Goring, and from omega tensor sigma to the Goring in the Waiachi-Pepe setting. And then this turns out to be a morphism of comonads. And by a morphism of comonads, I mean here, in this situation, a two-cell that preserves the structure. And you can also do this in the dual sense. You can look at a monad on A, and then write A actions on M correspond to left actions on N. It's of course just a dual thing. And then you can do that also for the monad associated, and then you can describe these two actions. You have an action in the corresponding one. And then you also have the dual of the canonical map, which I usually denote by NAC.
So this COCAN. COCAN is
Yes.
What is CAN-CAN?
But in order to compare with the classical situation, I will restrict attention to the comonad situation. Okay. So, to the general situation, I take a left C-call module and a right C-call module. I need objects on the left and the right in the two situations. So these A and C are arbitrary, so B in the middle, that has to be the same in the two cases. So a command on C. And then, if it exists, and this is an assumption, we'll come back to this. If it exists, then you can consider the equalizer, and that is called the co-tensor product. And it satisfies a universal property. If you have an X should be the category A, C, and a map from X to Mn, such that the two compositions here coincide, then you have a map here. The usual definition. Of course, in general, you don't know whether this exists. But assuming that it exists in enough situations, then it behaves functorially. And from the universal property, so if you take another object P, here NP, I don't write the brackets here, but you could write brackets here. So then there is a unique alpha between M tensor Cn, then composed with P, and then M cotensor NP.
So this is a kind of generalized cotensor product.
Yeah. And just generalize the notion of cotensor product. You can do that formally. That's in fact all that I do. But of course, I don't know whether it exists. But let's assume that it exists. There are situations when it exists. If you put C for one of them, and C cotensor over Cm is isomorphic to M. You can just prove directly that. And you can do even more. You can put PC here, cotensor C, with the coaction on C induced by the co-multiplication. Then you also obtain just PM.
So how would you get the usual cotensor product by substituting what for what? You can
I do that already at the level of co-modules of a co-algebra. If you have a right C module and a left C co-module,
yes.
you can take M. Let me go back. You can take M tensor N, and then you can apply the rho to the first, and then you arrive at M tensor C tensor N.
Okay.
And you can do the same thing
Okay.
on the left.
Okay.
And the co-invariants that I introduced before, they are of course an equalizer, and they are cotensor products.
So therefore, it's better to call them invariants of the coaction.
Exactly.
Because it's
But there are two coactions.
sorry?
There are two coactions.
Yes. So this making them equal, okay, it's like passing to the sub-object. So this like
Not the quotient object. Covariance imply that you have a quotient object.
in homological algebra, invariance is a sub-object. Covariance is a quotient object. It's like balance tensor product, for instance.
Yeah, this is not my responsibility. But you know, I had to look this up. So you have an equalizer. The Abelian category is the kernel of the difference. But do you call this an equalizer or a co-equalizer? It's called an equalizer. And then if you take a co-kernel of a difference, that is called the co-equalizer. I looked it up, and this is, I think, what I maybe also different terminology is used there.
So the co-equalizer is a dual notion
Yeah.
to equalize. So
You can do the same thing, of course, for an algebra.
So in fact, there are two levels on which, if you have two categories, you have two levels on which you can dualize. So sometimes people call one dualization op, and other dualization is called co, to distinguish them. And there are many versions of op, co, op, co-op. Yeah.
I will illustrate that on a
Okay.
with a construction. Okay. Now, you take an adjunction, you call monad, and you assume that on M there is a left coaction, or equivalently a right one on C. Then this should be okay, it's okay. In this situation, you have an adjunction. You take an arbitrary X, and once again, if you look at vector spaces, then there's only one X, which is K, so it doesn't matter. And for Fx, you take Xn with coaction introduced by rho, and it has a right adjoint, which is given by, so y sigma is the right coaction on y, and then you take the cotensor product. And you can even describe the unit and the co-units of the adjunction. You have to assume that this cotensor product exists. So we start with an object X. Then you take Xn cotensor Cm. So there is, using the universal property, you have this setting. If you take X theta here, theta the unit of the adjunction, then you have equality of compositions, and then you have a unique map, which is the adjunction. And a similar thing, well, it's not entirely similar for the co-units. So you compute that fg of y. This is y called SOCM times n. So you have this associativity here. We have seen the existence of this map alpha already. What you do, you have I to ym. So this I and this I are not the same. But there are not enough letters to distinguish between all of them. But anyway, you have commutative diagram here. And then you can apply epsilon here, and then you land back in y. So the composition y epsilon after in is the co-unit map. And you can also describe it using this map alpha, which is the one given by the universal property.
I have a question about this, let's say, equalizer. Can you somehow cancel this x from everything?
Mhm.
Practically in algebra, this x is not necessary.
What you can do, so n you can replace x
Yeah.
by a, by the unit on a. Then you have capital AN, and this is n.
So you can make this condition free from this x. And this would mean, this would make this construction closer to the potential product. Because this would be the universal property of
You
because-
have to be careful, because if you then want to have the x back again, then you have to put brackets here.
it's like putting, okay, so it's like putting parentheses. So now x is in parentheses with n.
Here,
Yeah.
it's here.
Mhm.
So
So
you,
this is different from putting x in parentheses with this potential product in a
Yeah.
sense.
but what you can do, of course,
Ah.
you can put, and we will do that in a second, you can put x equal to small, to capital A. So x has to be in x, A, round A, capital A. You can put capital X equal to A, and then you can take the unit. And then you have this, that you have it. So in one direction it works,
Yeah.
but in the opposite direction, not in general.
So this means that somehow something here is not associative. Different distributions of parentheses could give you something different.
Yes, yes. And this is what you have already in the classical situation. And this is maybe the reason why I work on the co-monad level. You can do it for monads also. And then you have exactly the dual of this. But if you do that, and we will see that later on. If you look at bimodules, and you have algebras, and then you can look at rings, which are algebras themselves.
Yes.
But this is why algebras and bimodules, they form a two category.
Isn't it related to the fact that tensor product in some concrete category of polynomials is right exact always?
That has to do with it, yes.
And you can not dualize it for comonad. You cannot say that
Of course,
product is
that classical tensor product is right exact.
Yeah.
That induces that, but in the general setting, you don't know.
Yes.
So, and this will be one of.
So you need some flatness or co-flatness conditions for monads and for comonads.
But wait, standard tensor product is left exact.
Over a field.
Yes.
Over a field?
Yes.
Yes. Only over a field. Not in general.
Yeah, so not for co-rings.
Yeah.
This is why in classical situation, in this, but
25 minutes.
hmm?
Yes, 25 minutes.
Yeah. But okay, I will come back to this later on because that's okay. What I can do, so taking special cases for the co-unit map, I get exactly the canonical map. And for the unit map, if I put x equal to a, so this is what we were talking about. In this situation, so the unit map satisfies this. And you can conclude from that if f is fully faithful, that means all these etas are isomorphisms. That means that A, eta, and M, so then you have isomorphism here, that this is an equalizer. G fully faithful, that implies that the canonical map is an isomorphism. So this is at least part of the things that we cover. Now what you can do, so I call this cometric scoring again. So you take C equal to Mn. And Mn as before, you can describe the adjunction. And then the canonical map is the identity. And you can describe when the unit map corresponding to X is, so this is a general one when it is this equalizer. Now, and the same thing you can describe for the co-units. And then we have a kind of associativity conditions. We have seen this map before. And then if you have a pair of inverse equivalences, then this needs to be an isomorphism. Now, and there is something, and I try to do this, maybe somebody did this before, but of course, so you can consider.
So this is condition for associativity in a sense.
This is yes.
Yeah.
You can do similar things. Let's say we think about only tensor products, but then not over the trivial monads, but also over the general monads. You could hope you can introduce bimodules between monads, and you could hope that these establish a two-categorical structure or bicategorical structure on bimonads. But for this, you need the associativity of the tensor product, which you have for classical bimodules, obviously. But of course, in the general two category, you don't have this. This map, but in the general case where you put a C here or an A here, and then below, if you assume, then you have a map in the opposite direction, of course, because you are in a dual situation. If you assume that in all situations this is an isomorphism, so that you have the associativity, but at a level where one of the two tensors is over the trivial monads, then I can construct maps from M tensor N tensor P to the other one in general, and in the opposite direction, because that's of course a general construction. But I cannot prove for the moment that these are each other's inverses. Now, I don't know whether it has been studied, what are sufficient conditions. Under the assumption, of course, that all the equalizer or co-equalizers exists. And this will come back in a second. Because now I come to the construction of streets. So he takes two categories and he organizes monads into a two category, which is exactly what I wanted to do using bimodules. But he does it in a different way and in general, so it works in full generality. So you need to construct a category A prime mon A. And what is an object in this category? It consists of a couple U phi, and then where U is a one cell in A prime AA, so a one cell from A to A prime categorically, and then a two cell from A prime U to U, and this should be to UA. I will erase this. Is this 20?
No,
No, it's okay. It's okay. Another A.
Yeah, the next A is stands for
Amorph.
Exactly.
Amorphous. Oh,
it's an article, yes.
should have introduced the line break and two commutative diagrams. And the ones that you more or less expect. And then two cells, a morphism. So it's a morphism between the underlying one cell of the one cell, and also such that the diagram commutes. Then we have to introduce composition of one cells, which is the difficult thing if you work with bimodules. But you can do it. So here's the description. U prime phi prime U phi. The level of the one cell, it's U prime U. And then you can see that phi prime U, and then you do U prime phi. Makes sense. And that's what you do for the composition. And then a similar thing at the level of two cells. Here it is just the ordinary compositions that you have to take. And then you have to prove that this is a two cell between those two cells, but this works out. And this creates a two category, and this is the.
Sorry, but these two cells now are regarded to be one cell in one cell in this world. Okay, if this is two cells connect one cell. So what was before
No.
two cell now becomes in this moment one cell.
So the zero cells are the monads.
Yeah, so there's a shift in the dimension of this cell.
Yeah. Oh. And this is a construction like this, which is what I mentioned, I can do for adjunctions. So for adjunctions, you can do different things, but indeed, as you said, so the one cells, they consist of a one cell and a two cell. And the two cells, they consist of a two cell with all kinds of compatibility conditions. And now, one of the constructions is, so there is a second category. And that is called the Eilenberg-Mohr category. And there, the zero cells and the one cells are the same. And now for the two cells, you don't take a two cell from U to U tilde, as before, but you take one from U to U tilde A. Right? And again, with the
So it is
commutative
very similar to the previous case. It's like you have two monads. One is identity and one is A. The condition is the same. One composed with U goes to U tilde composed with A.
but there is, so the composition is a little bit different. The composition was just composition, the composition of two cells is different, but you get a second two category, and there is a two functor.
This explains this.
And there you send sigma to sigma iota. And iota is the identity of the map. Okay, so there is a choice between left and right between them, as you can see. Which one is the good one? And you have different things. You also have monads on A star. And what is A star? So now I come back to the question that you had before. So in a two category, you can reverse the one cells. So that means instead of taking the category from A to B, you take the one from B to A. For determining monads and comonads makes the same, makes no sense, because if A is equal to B, that is the same. So if you look in this category where you keep the two cells the same way, then you get as objects, so the monads in A star are also the monads in A. You can, in this notation of street, you can also take star below. This is where you reverse the two cells. This is where you replace A, B by A, B up. Then the monads become comonads in the original category. But so that is different. You can do that also. You can do this, all these games with monads also. Okay. As I said, under appropriate conditions, you can consider bimodules. So this is maybe a bad name because it refers to the one cells, where the underlying categories are the bimodule categories. But then you need many conditions. So for vector spaces, it works. It works certainly for other categories. I believe that if you take Hopf algebra and if you take modules of the Hopf algebra, we know that it's a model by the category. So this is a two category with, or a bicategory with one object. Then I guess there will be no problem. So, but in this case, so you have 5 categories. You can ask what is the connection between this construction and this construction. Maybe this is folklore, but at least I rediscovered it. So the explanation is the following. If you take a bimodule, if it is of the form UA with a left action and a right action of the form U mu, where mu is the multiplication, then we call this right free. You can do the same thing at the level of morphisms. So a bimodule form of the form sigma A between two free A prime A bimodules, we call it free. So you can consider the following two subcategories of A prime A. What you can do is you can take the full subcategory consisting of right free bimodules and bimodule morphisms. And then you can take FF, right free bimodules, and 3 morphisms. And then it turns out, if you take the double free case, that is exactly the model construction of street. And if you take only 3 at the level of one cells, that is the Eilenberg-Moore construction. And it's isomorphic, so you need to be careful a little bit. So here's the proof. We take a right free module. From this, you have a map from A prime U to UA using the iota. And this gives you something in non. This is exactly what you need. And the converse construction goes like this. You do phi A. You start from this phi. And then you have two A's at the other side. So you go from A prime U to U A times A, and then you do multiplication. And sigma from U to U tilde defines a two-cell in non-A between the three modules. So these are all verifications. And a morphism from U to U tilde A defines a two-cell in the Heisenberg-Moore category, if and only if. So you also have to make it a map from UA to U tilde A, which you can do in the obvious way, and then you get bimodular morphism. This row is this row, or is this UA? This is this row. It's not a coaction. Simply this row. Okay, and this explains things in a way. So what was the problem with bimodules is that the tensor product, if it exists, even if it exists, it does maybe not behave well with respect to associativity. But if you take three modules, and I had a similar property, but then for the cotensor product. So then U A prime tensor A prime U prime A tilde is equal, or at least isomorphic, to U prime A tilde. You can do that by proving that U prime A tilde satisfies the universal property that you need, which is the straightforward thing. So that means that you can start from monads, and then you take right-free bimodules, and then you can construct a two category. And you can do it in two ways. With the morphisms, you can either take free ones or general ones. So that gives you these isomorphism categories. So this, well, two categories, this is bimodules, but free, and here free. And of course, you can do that at the other side, and then you have here the same constructions within A star. Okay, what's the next thing to do? This mon A is a two category. You can look at comonads in here. Let's do this. You need a one cell. Okay. So one cell is a couple C phi. Then you need a co-multiplication and a co-unit. Okay, so this is in free, so this is in monads. So these two cells are usual two cells. So it means if you forget the two cell conditions, you have usual two cells, you have obtained immediately that C is a comonad. You can write down the conditions that the epsilon and the delta are two cells in the category of monads. Gives you these conditions. What does these conditions mean? That means you can look at A phi, but as a morphism from C to C in comonads, but over A star. Everything becomes quite dual. What is a comonad in mon A? So it consists of a triple AC. A is a monad, C is a comonad. And C phi establishes a morphism in monads of A phi establishes a morphism in comonads A star. This is exactly an entwining structure, but not entirely in the same way written as in the classical papers by Brzezinski and Majid, because there they have right entwining structures or right entwining structures. These are the left ones. This is because I started from the conventions of streets. If you work with a star, then of course you have the other ones. You can describe the corresponding comonads. So you get a right free bimodule. This is CA, and you can describe the module and the comodule structure. Of course, the right module structure is C mu, and the left one you can describe from the construction. It turns out to be C mu after phi A. The multiplication introduced by delta, and the same thing for the co-units. And you see, this is the categorical version of the construction that was established by Brzezinski and Majid. I should mention there is an old paper on archive where part of this is done. It is one by Zoran Skoda, but it never appeared in the literature. And in the introduction, he mentions that Gabi Böhm told him that but this was then at the level of classical bimodules, that entwining structures are exactly the comonads in the two categories of streets. And there's another version. You can look at factorization structures between two monads, and that gives you the monads in monads. Okay, now I can do algebra Galois extensions, so and I should
have 3 minutes.
Okay. So I take a monad, and then I take two bimodules. Both of them are free. A is right free, and then A, but on the right-hand side, viewed as a capital A, as over capital A is free, because capital A is the same as A. Then you can take the tensor product. This is AA. You take the other tensor product over A. This is A. And then you get an adjunction in the Eilenberg-Mohr category. It is an adjunction, so it is an adjunction, but not in the monad category, but in the Eilenberg-Mohr category. Because you can see that the connecting morphisms are not free. And you have an associated comonad, and that comonad is precisely the equivalent of the Spiegel canonical curve, which is also a comonad, but it's not one coming from an entwining structure, because it's one in the category with a single F. Okay, then you can proceed, you can apply all the things that we did. Now you don't have problem with the cotensor product. I have to finish. So you can look at a general. You can look at the comonad coming from an entwining structure. So this is one in the FF category. You can look at actions. What I do is I take lambda after I, that goes from A to CA, that is gamma, and that turns out to be an equivalent of of a group-like element. So it establishes a coaction if you have a group-like element. And you can do the same thing on the right. It is different, but you can do it. It gives you different results. And the right co-action after the iota, this is a iota, gives you also the group-like element. Then you can describe the canonical map. So this is a map or a morphism between three modules, three bimodules, or right three bimodules, but it's not, the morphism itself is not free. Maybe I should have written it with Greek letters here, gamma, alpha, nu, because the two-cell needs Greek letters, but okay. And then you can describe the left co-modules. So I won't do this in detail, but turns it out to be. This is a left A module and a left C co-module satisfying a certain compatibility condition. And these turn out to be the entwined modules of Brzezinski and Majid, but on the left-hand side instead of the right-hand side. You can also look at the right-hand side and you can describe the adjunction. You need a kernel, but you can do it and you can do it at the right also. Okay, I will stop here. The next thing would be to look at Frobenius monads. Then the intention is to simplify everything. There's a very symmetric definition to exploit that in a general situation. This work has not been done completely. It's done in the classical situation. Most of it was known, but the formalism can be used to put it in a better situation. You can do that if you assume that the bimodule 2 category exists. Then you can also use the Morita contexts, and then you can simplify the theory, and then you can do some structure theorems where you really have equivalence of categories without having to assume that you have some flatness conditions which follow automatically from all the situation, as in the classical case, where you return to the original situation. If you look at group Galois extensions in the classical sense, then in these definitions, not in all of them, there is a flatness condition involved, so you can go around it, and then you have it automatically. Okay. And
thank you very much. Time for more questions. Maybe I will begin with experts. Claudia, c'è una domanda? You have to unmute yourself. You are still muted.
Please unmute.
I cannot unmute you. You have to do it yourself.
She's gone.
No, she's there.
Wrong button.
Yeah, it's the button next to the one that was
Wrong button.
yeah, it's the other button, the one on the left.
Okay, so while we wait for reappearance, anybody from the Zoom who wants to ask a question?
There were two, I think.
No, these are classic hands.
Okay.
Adam, do you want to ask a question?
So,
No, I don't have any question. Very nice talk, thank you.
So you categorically deny my offer to ask a question.
No, by category.
Maybe you should make an offer to ask a two question. It would be two categories.
Yes. Okay. Nobody from Zoom? Anybody from the room?
yeah, maybe I have a very naive question. You talked about comonads in Mon, and you get this description of entwining structure that in a special case gives you tensor product of coalgebras, gives you, right? How to put a coalgebra structure on some kind of... So can you do the opposite? Can you consider monads in con?
Yeah,
And
Completely symmetric.
it's completely symmetric, okay. And you get what you expected. And
general theory.
factorization of algebras, okay.
But the thing is, so it comes from different sources in the literature.
Mm.
And so I start from the street condition, and you arrive at the left entwining structures.
Yeah.
Where in the Magic Brzezinski, it's the right entwining structures, but you can see that easily see that it's the same.
Correct, no?
Okay, okay. Let me start with some anecdote. Okay,
It's not too long, please.
in times of the French Revolution, when Marquis de Sade
Oh my
was freed from Bastille, he was running along the streets saying, citizens, let's do one more effort, introduce the free love. Okay? Okay, so now I can come back to mathematics. So the formal theory of monads of street is like this French Revolution. So what about making one effort more? Because at some moment you are building some diagrams. You are proving that the same diagram can be built vertically and horizontally in two different ways. And this is the proof, your proof of equivalence of some, or two equivalence of some two categories. Okay? What about doing second revolution of double categories in which you could speak about a formal theory of formal monad theory of street?
Ah, you mean to do the formal theory of
Yes, what you are, because everything you are doing this on the level of the formal theory of monads. Okay? But you see, even you have some diagrams which are rotated by 90 degrees. These are the same diagrams.
the diagrams are the same.
So this means that you are building the same diagrams on the level of two categories, once vertically and once horizontally. So it's a different interpretation. But this could be made even more formal if you do something in double category, in which you have existent these two independent directions. And of course you will need some middle exchange laws to compare this.
You mean?
Yeah.
So you could start looking at these duoidal categories of Galois.
Yes, you
have.
Yeah. Because at the end of the day, your proof is like this. You are doing something vertically, something horizontally, and you have the same result. So this could be also formalized.
For these entwining structures, you mean?
Not only for entwining structure, I mean this equivalence between, if you could come back several pages to see one of these equivalences, okay? These are,
Between the free.
no. In the title of this page, you should have some equivalence. Okay. For instance, like this. Oh, yes, things like this. So left-hand side is defined by some diagrams. Right-hand side is defined by some other diagrams. But in the proof of this equivalence, you are showing that these diagrams should be built first vertically and next horizontally. On the other side, you are doing this in the opposite order. And look at your diagrams. For instance, diagrams are very important here.
It was before. It was before.
Yeah. One was before and one was after.
Like a motion picture.
Yes, can you see? So this diagram is a diagram you considered before, but it's rotated by 90 degrees. So now it's done vertically. Before you were doing this the same horizontally. But now you have this one kind of composition, before it was another kind of composition.
I don't know whether
There must be some reason.
vertical and because if so, all these definitions.
Mhm.
So there is always a compatibility, and that you give by a commutative diagram. But the same commutative diagram. See, which one is it again?
0.5 go to right, yes.
So you can write alpha, beta, gamma, delta. But you can also put gamma here and alpha here and beta here and delta there. That makes no sense. And it is, so it might happen that by accident, one of the definition of two cell, so you copy it and you get this. You write it out and you get this. And then that is, if you want to, and then the definition that would be given would be put in the other, but it doesn't matter.
Yeah. So what is compatibility in one direction? Okay, horizontal or vertical. Okay. If you rotate it, it becomes a morphism, and what was a morphism becomes compatibility, kind of compatibility. It's my impression that there is some symmetry here in this reasoning, and this symmetry could be formalized on some level of maybe double categories or duoidal categories.
Could be.
And the only thing which will be important is something which is called this day middle exchange law. Okay.
That is what you have in the definition of the duoidal category. It's clearly presented.
Yeah. So this is very beautiful. It is very far from the classical context. People are doing this Galois theory, for instance. But still is not the end of formalization. Even this could be made formal on a higher level. And that's my impression. That is only an impression.
So I ask you a very, silly, naive, provocative question. So what's the upshot of going to this level of abstraction? What do we gain? What understanding, what better understanding we have in some concrete applications?
It's a simplification of the conceptual level for the price of a higher abstraction, as usual in mathematics.
Okay, so you just, common denominator for many different constructions, and then you see what they have in common, right? But does it allow you, by recasting your point of view, does it allow you to solve some previously unsolvable problems?
You can formalize your proofs easier. Because in higher categories, your proofs are so complicated that they become maybe not conceptually difficult. They are difficult computational. So if you can avoid computation, replacing them by abstract arguments,
no, this is of course
it's a big gain.
And has anyone proved something substantially new this way?
There is a business of doing mathematics for more and more formal.
I mean, once it's formal enough, so you give it maybe to artificial intelligence.
Will do the job for you then.
Yeah.
AI.
Yeah, yes. So we are. This is a preparation for our inheritance, which is
your Tesla will.
So humans are doing this job to pave the way to the next generation of mathematicians, which will be AI.
Oh, well,
Which will
so maybe indeed, there are examples, maybe not this generalization, but if you look at the previous one, the Galois theory of Collins that goes to Brzezinski, and maybe to Takeuchi even, where you take this answer A. And so the first thing that I saw this. So this was shortly after the coalgebra Galois extensions. So once I gave a lecture, and then I believe it was Iguzain taught me coalgebra. No real examples. But still, when I saw this first, the computations there are much easier than if you do them in the situation of Hopf algebras, and all these arguments become suddenly natural. And if you look then at co-rings, they become even more natural. I remember that when I first saw it, I wrote an email to Tomasz Brzezinski telling, it's amazing how simple this becomes. So it gives you a real simple, and in mathematics today, there are many examples. I think if you look at the definition of a quasi bialgebra and a quasi Hopf algebra, you can just formulate it algebraically, and then you can do computations. It is perfect. And maybe at the beginning it was done like this, but there are conceptual definitions. So you have to use monoidal. So you want to have you have an algebra, let's say, and you want a monoidal structure on the category of algebras and turn it into a bar algebra. That is a possibility. But then you can relax this a little bit, and then you have precisely the definition of quasi-bar algebra.
Yeah.
And
then you understand what is going on.
Yeah.
And if you think, for instance, about even the level of co-rings, you have a book of Brzezinski and Wiesbauer.
Yeah, not that.
Okay, Lord of co-rings.
Yeah.
This comes from this. Yeah. Now, all this theory becomes few pages on this level. All this book can be comprised to several pages.
Well, I'm not. Well,
maybe I'm okay. Allow me. I'm quite exciting with what you look for. It's not convinced. So please allow me this exaggeration.
Your favorite environment, the last page.
Yeah, you print like your pages.
But it's not so much.
Okay, I appreciate all these arguments and examples. However, I must respectfully point out that my experience with going from Hopf Galois to coalgebra Galois was quite the opposite of what you are saying. Elmar is still right here, and when we generalized one subjective pullback Hopf Galois theorem to coalgebra Galois, things were far more complicated and difficult. And basically what happened that things that coincided in Hopf Galois theory, you just get one map with properties. All of a sudden our diagrams required 5 different maps because everything was different. It still could be put together, which showed that this initial problem was natural because it allowed us, we could solve it at a much higher level of generality, and the basic idea still worked, only they were technically far more complicated. So I'm not so convinced, and doing a lot of calculations with entwining structures is definitely far more complicated than working with modular algebras.
By the way, this is a final remark that I would like to make, something that I have in mind to do. So there are entwining structures, but there are also weak entwining structures. And maybe there is another by category of monads.
We start weakening.
But if I might continue, we didn't torture ourselves with Galois theory because we wanted to be more general or have a bigger common denominator. It was forced upon us by examples, by very natural examples.
I know it came from a different direction, but then it turned out. Because initially you were not trying to generalize.
No, not at all. We're trying to. We are very unhappy that Hopf Galois theory would exclude our beloved examples.
Yeah, there's all, okay, we had this discussion many times. So with examples, there's a problem, which is called the Quine indeterminacy of a theory, which is a very far philosophical extension of this principle that if you have several points, you can find many graphs going through this point. So every example is concrete, and it can have properties which are important for one generalization, but also carries some properties which are accidental to this theory.
Yeah.
Okay, so if you start from a limited number of beloved examples, sometimes these accidental properties of these special examples go against what is really going on.
Yeah, but this wasn't the case here because it was the whole family of natural examples.
But naturality is a tricky question.
Well, it comes from Poisson geometry and so on. So
Yeah,
so that's it was a whole mechanism, not just one beloved example.
The colloquial naturality is one thing. To make it formal and categorically natural, it's a tricky thing.
Well, I mean, yeah, there is the whole geometrical theory which can be comprehended with algebra Galois and cannot be comprehended with Hopf Galois. That's for me good enough. But let me ask you, because the time is running out and the dinner is getting cold. So, yeah, and beer is getting warm. So I don't know really how to formulate my question because I'm lost in realm of two categories. But you mentioned two things that are quite dear to my heart. One is canonical map, and one is entwining structure. But you see, one of the things that we did with Tomek Brzezinski when we introduced algebra Galois terminology was that we proved that there is a canonical entwining structure that is not an additional input data, as was initially assumed by Brzezinski Majid. So I'm wondering if in your language we have both the canonical map, which I presume you can assume to be an isomorphism, whatever meaning, and I have an entwining. Can you point to me what would be the canonical entwining for the canonical map being bijective? Because we basically constructed this entwining out of a canonical map, and we proved that it's the only entwining that does the job.
Yeah, I remember having seen this, but
So I think me and Francesco could answer now this question. So the point is that to make this theory of Hopf-Galois functorially enough, you have to put by hand or take it from general distributive law theory. You have to put this and not entwining. In fact, it's a braiding. Yes, algebra factorization. And then it turns out that what was necessary to define some diagram in the category of algebras, in the Hopf-Galois case, becomes so rigid by invertibility of the canonical map that it is determined unique. Okay. So this canonical entwine or canonical Jurjevich braiding, this phenomena, okay, these are results of invertibility of the canonical map. But forget about this Galois condition. You can speak about diagrams which commute in some categories, but then there is an additional datum, which is some kind of twist or some factorization structure for an algebra or some entwining for a coalgebra. Or a coalgebra with respect to this algebra, so usual entwining conditions of distributive laws.
Yes.
Okay. So distributive law or mixed distributive law on this level seem to be a necessary part of the structure. But in the Galois theory, they are unique. So you can produce them from this invertibility of the canonical map.
Okay, I'm happy. I'm happy with this answer. Yes.
But this is rather an exception than the general rule.
Sure. No, I'm not claiming it. It's strictly a Galois phenomenon.
Yes. But it's a part of something more general, which makes sense.
But how do you arrive at the canonical map then?
Sorry? No. For instance, this condition of this canonical map, for instance, being an algebra map, which is not part of your theory. Okay? But in the Hopf-Galois theory, it is so. In classical, it is so, not in your theory, but you can force, in Hopf-Galois theory, you can force this condition that the canonical map is an algebra map. Okay? So you can interpret this in two ways. First, you could compute, like in braiding, in A tensor A over B.
Yep.
Or you could add this twist or braiding between these two copies of A. You could take it as a part of a structure and formalize this. After this formalization, it turns out that in the Galois context, this additional datum is unique. It's uniquely determined by the Galois condition.
Yeah. Okay, I think it's
It
fine.
might be related to what we have here.
Probably, I'm not so sure because, oh yes, on this higher level, when you are regarding this monad as, algebras as monads on the category of modules. If you have an algebra B and you have the category of left B modules, then the algebra A with a morphism from B to A becomes a monad on the category of B modules. So your theory can be applied to this. So probably you're right. You could speak about this on this two categorical level. Yes.
So my question might have an answer.
It can have some formal answer, but it has a concrete answer in what we are doing.
Okay. And this is a good conclusion for the seminar. Let's thank our speaker again. Not in the chat, so just let me quickly. Sorry, I have to leave. Ciao. So Claudia says ciao, and I stop recording.